Okay. So, questions from you guys. Palmer? Scroll up to number 9.
Yeah.
Oh, yeah.
Thank you.
You're welcome. Addie? Sure. So 11 is the square root of 112 over the square root of 147. So the first thing I'm going to do is I'm going to do a prime factorization. So for 112, that's 2 and 56, which is 7 and 8, and 8 is 2 and 4, and 4 is 2 and 2. So this is 2 to the 4th times 7. Okay there? Next up is 147, which is 3 and 49, and 49 is 7 and 7. Good there. Okay, now let's try to do our exchanges. So in the numerator, I have a 2 to the 4th. The exchange rate is 2, so I can take out 2 2's, leaving me with no 2's left over, right? I can't do anything with the 7, so that's still just going to stay there. Now I'll move to the denominator. There I notice that I have 1 3, but my exchange rate is 2, so I can't do anything with the 3. So that's going to stay there. And then I look at the 7. I have 2 7's. The exchange rate is 2. So I can move 1 7 to the outside. We okay there? So we are done reducing, but we had said that we didn't want to leave our answers with radicals in the denominator. So you'll notice right now that we do have this square root of 3 in the denominator. So that's the problem. That's what I'm going to fix now. So if I had 2 3's under that radical, I could cash both of them in and I have nothing left in the radical, right? So that's going to be my plan. Right now I have 1 3 in the radical. So I need a second 3 in the radical. So I'm going to multiply the top and bottom of this fraction by the square root of 3. So in the numerator I have 4, and then 7 times 3 is 21. And in the denominator I have 7, and then I have 2 3's in the square root, which I can trade in to just give me 1 3 outside of the square root with no 3's left over. Does that make sense, Addie? So I really down at the bottom, I just have 7 times 3, which is my 21. And there's my final answer. Henry?
Can you explain how you got like the 2 to the 4th times the 7 over 3 times 7?
So my prime factorizations for those numbers are right here.
Yeah. So then, like, how do you just like find out that's 2 to the 4th times it by 7?
So if I look at my primes, I have 1, 2, 3 4's, and then a 7.
Okay.
And then if I look at the other one, I have a 1 3 and 2 7's. Is that what you're asking?
Well, yeah.
Okay. So again, I'm drawing these factoring trees or doing it in my head if I can do it in my head. Some of them I can. Some of them it's not as easy. But I feel like for you guys, me writing it down is often helpful so you can see kind of what happened. Kate. Okay, so if I have 4 quarters, or if you have 4 quarters and I'm the bank, you can give me 4 quarters and I give you back a $1 bill, right? So here the exchange rate is 2 because it's a square root, right? The index here is 2. We don't write it there, but we know it's there. So here I have 4 of them. So I can trade in all 4 of those 2's underneath the radical to get 2 2's outside of the radical. Because that's how the exchange rate is. It's 2 to 1. Okay, so that's kind of the way I'm thinking about it. Okay. Oops, lost that 7. Okay, good. Should we do another? Does anyone else want to ask about any of these? Happy to do more. Caden? 15? Okay. All right. So I'm going to start by finding the prime factorizations. So how can I split up 88? Okay. 11 is prime, so there's nothing more to do with that. How can I split 8 up? Okay. And then 4 is 2 and 2, right? So I'm going to have 2 to the 3rd times 11. Sound good there? Okay. Now let's do the 208. How can I split that up? Well, it's even, right? So I certainly can divide it by 2. 2 and 104, right? Okay, 104, can I split that up? What into? 2 and 52, great. And then what? $26. Any more? 2 and 13. And 13 is prime, so we're done. So I also have a 2 to the 4th and a 13. So I'm going to just write that under one radical there in the numerator. So far, so good? Okay. Let's do 99 now. Okay. And then 9 is just 3 and 3. So I have a 3 squared and 11. Then 819. Two doesn't work because it's odd. But if you look at the digits, 8 plus 1 plus 9 is 18. And 18 is divisible by 3, so I know 3 is going to work. It's actually 3 and 273. And again, if I look at the digits, 2 plus 7 plus 3 is 12. So that worked. And this is 7 and 13. We okay to here? So look at those two radicals, and I notice something right away. This is the first thing that I would do. Just do a little bit of reducing. That makes life quite a bit easier. So really, I just have 7 2's in the numerator, and then 5 3's and a 7 in the denominator. Caden, you good with this? Okay. How many 2's can I take out of the numerator? Well, I get 2 2's on the outside. How many are left underneath? 1. So if I had like 9 quarters and I went to the bank, you get back two $1 bills and you still have 1 quarter left over, right? So we have 7 2s and we need 3 of them to make 1 full 2. So I can do that twice, right? And I have 1 left over. Is that?
Yeah, so the ratio changes.
You kind of mumbled that and I missed what you said. Yes. Yeah, so the 2 numbers you're looking at, you're comparing the index and the exponent. And that's telling you, that's the numbers that you need to look at. How about the denominator? Oh, that should be a 4 there, excuse me. Right? I have 2 3s and then 2 3s. Sorry. How many 3s can I take out? 1. How many are left over? Okay. And can I do anything with the 7? No. So that's that. Now all we have to worry about is this radical in the denominator. So, in order to get all those 3s out from the out from the radical, how many 3s would I need underneath the radical? Three of them, right? How many do I have under there right now? I have 1, right? So I would need how many more? 2 more. If I do the same thing with the 7, I'd have that. Caden, are you okay there? Okay. So in the numerator, I have the 2 squared, which I'm just going to write as a 4. Then I have 2 times 9 times 49, which is 882. Are you okay with where I did that? 2 times 3 squared times 7 squared. And that's the 882. Is that good? Okay. In the denominator, I have 3 3s. So that's going to pull one of them out. This 3 is that 3. And if I look at the 7s, I have 3 7s, so I can take one of those out as well. So that gives me 3 times 3 times 7, or 63. Is that okay? What do you guys think? Any more questions on this sheet? Henry?
Can you just do 5?
Sure. Okay. So I'm going to start with the prime factorization of 1620. So it's even, right? So I can do that. And maybe 8, 10 is 81 and 10, maybe.
And do you just can you just choose any of the factors that you want?
Yeah, as long as the 2 numbers multiply, it doesn't matter what you're doing. So it doesn't have to be the same ones that necessarily I would have picked. What's going on here is it's actually called the fundamental theorem of arithmetic. And it says that every positive whole number has a unique prime factorization. So that means is any way you do the prime factorization, everybody should be getting the same answer. There's just one answer to that problem. So it doesn't matter which factors you use to break it up, you're going to end up with the same prime factorization, the same powers of products of primes. So let's see, I have I have 2 2s, 4 3s, and a 5. So if I look now to see if I can take anything out, I only have to do an exchange, I need to have 3 of something. I have 2 2s, that's not enough to do anything with. I have 4 3s, so I can get a 3 out of there. That leaves me with 1 3 left. And I have 1 5, and that's not enough to do anything with either. And so the last thing I would do is just multiply this stuff together. So 2 squared is 4, times 3 is 12, times 5 is 60. Does that feel okay?
Yeah.
Chloe?
Wait, fraction.
You can ask your question, it's okay. No? There's no such thing.
No, you probably already answered that.
Well, if you need to ask your question, ask your question. Even if it's a dumb clarification question about something we just got done saying, it's okay.
Why did you take out the 3? If like, it's just y.
Okay. So if the exponent is bigger than the index, you're able to take something out. Okay? So what we're doing is we're subtracting the index from the exponent as many times as we can and still getting a positive number. I can do one subtraction, so 1 3 can come out. 4 minus 3 is 1, so that's how many are left after I do that.
Okay.
Is that?
Yes.
Okay. Did I do a good job? Was it better than it was before you asked your question? Then ask your question, it's okay. Go ahead. Sure. 7 sounds good to me. Okay. So we'll start with prime factorizations. 20 is 10 and 2, you said. Then 10 is 5 and 2. Okay. 36 is 6 and 6. And 6 is 2 and 3. So let's see, I have 1, 2, 3, 4 2s. And then I have 1 5 and 2 3s. So notice here with the multiplication problem, I can just take it all and stick it under the same radical. So are there any exchanges I can do? Yes, because the exponent on the 2 is bigger than the index. How many times can I do that subtraction? 1 time. 4 minus 3. I get a positive number if I subtract it 1 time. And then how many 2's are left after I do that subtraction? 1. Can I do anything with the 3's or the 5's? No, because their exponent is smaller than the index. We're done. So the last thing I would do is just multiply this stuff together. So 2 times 3 squared is 18, times 5 is 90. And that's what I would settle on as my final answer. You feel okay? All right. Can I ask you guys to take out a separate sheet of paper? You'll probably want your calculator and something to write with. All right. All right. So, continuing to talk about simplifying radicals. we've covered how we multiply two radicals together and how we divide two radicals together. What do we still need to talk about? Adding and subtracting. Okay, so we still need to talk about adding and subtracting. To add or subtract two radicals, they must be identical. What do we mean by identical? How about square root 2 and square root 3? Are those identical? No, right? Why not? Because the radicands are different, right? The number underneath the radical. What about square root 2 and cube root 2? Are those identical? No. Why not? Their indices are different, right? But when we say identical, we mean something like square root 2 and square root 2, where are exactly the same. Both the indices are the same and both the radicands are the same. Everybody okay there? Okay, so let's do some addition and subtraction examples then. So what if I have the square root of 2 plus 3 square roots of 2? So when we do this, the only thing that changes is the coefficient. So I have 1 square root of 2 plus 3 square roots of 2 gives me 4 square roots of 2. What does this kind of remind us of? Just adding variables, right? Like 1x plus 3x is 4x. You know what I mean? Basically the same rules. So what if I have 3 cube roots of 5 minus 7 cube roots of 5? What does that give me? Negative 4 cube roots of 5. Good. Everybody okay there? Okay. What if I have the square root of 2 plus the square root of 128? Can we do that? Oh, I don't know about no. I mean, not as it's currently written. But is it possible that, like, they reduce down to be the same radical? Yeah, it's still possible that could happen, so we have to check that. So if I do the prime factorization of 128, that's 2 and 64. 64 is 8 and 8. 8 is 2 and 4, which is 2 and 2. 2 and 4, which is 2 and 2. So this is really square root 2 plus square root 2 to the 7th. Okay, how many 2's can I take out of the square root of 2 to the 7th? How many times can I subtract the number 2 from the number 7 without becoming negative? 3 times. So I'll have a 2 to the 3rd that can come out. After I subtract 2 from 7 3 times, what's left? 7 minus 2 is 5. Minus 2 again is 3. Minus 2 one more time is 1. Can I add these? Yeah. So the square root of, 2 cubed is just 8, and 1 plus 8 is 9. Is that okay with everybody? Huh? 2 to the third? 2 times 2 times 2? Not 2 times 3, right? 2 to the third is different than 2 times 3. Cool? Okay. So let's say we want to do the cube root of 16 plus the cube root of 54 minus 3 times the cube root of 250. Can I subtract these or add these and subtract these? Not as currently written, but maybe after I do some reducing I can. So let's start by doing that. What's the prime factorization of 16? 8 and 2, okay. And then 8 is 2 and 4, which is 2 and 2. So I have a 2 to the 4th. How about 54? 6 and 9, okay. And then 6 is 2 and 3, and 9 is 3 and 3. So I have 2 times 3 to the 3rd. How about 250? Ten and 25? It's 2 and 5. That's 5 and 5. So I have 2 times 5 to the 3rd. Everybody okay there? So let's reduce then. How many 2's can I take out of the cube root of 2 to the 4th? Well, 1 2 comes to the outside. And how many 2's are left over? 1. Maybe I need to rephrase how I'm asking that, because I feel like you guys know the right answer and are giving me not the answer I'm expecting. What do I write for the next one? What's on the outside? 1 3. Okay. What's on the inside? Just a 2. All right. And the last one, what's on the outside? Yeah, I have the 3 that was there originally, so I have 3 times 5. And then what's left on the inside? Just the 2. So can I add or subtract these? Yes, because they're all cube roots of 2. So I have 2 plus 3 is 5, minus 15 is negative 10. Cube roots of 2. What do you guys think? Pretty doable? Yeah, it's not so bad. All right, we'll stop here.